Before I continue, let's review some maybe a few questions from our exercise. Let's say what is differentiation? As I explained last week, when we differentiation is dy dx, dy dx. For example, let's say uh, this just a review, review what we have done so far. Let's say, for example, we have this quadratic function. This quadratic function y equal to x squared minus 3x plus 6. And then the first derivative or the first differentiation pembezaan pertama we can write as a dy dx or y prime. This is equal to, okay, x squared. The first derivative of x squared is 2x to the power of 1, or 2x, only 2x. And then minus the first derivative of 3x. The first derivative of 3x is negative 3, because the first derivative of x is equal 1, and plus for constant, the first derivative of constant is equal 0. So the answer is 2x. The first derivative of y of this function is 2x minus 2x minus 3. Okay, that is for the first derivative. And then we also can calculate, can find the second derivative, third derivative, fourth derivative, and so forth. For example, the second derivative of this function, y double prime, this is equal to 2x. Sorry, this is equal to 2, because from the first derivative we have 2x minus 3. The first derivative of 2x is 2, and the the derivative of negative 3 equals 0. So the answer is 2. And then the next derivative, the third differentiation of 2. Now we have constant function. The first derivative is 0. Okay, that is the one of the question. How to find the derivative of any function, whether there is a linear, quadratic, or exponent. Please remember, if you refer to part A for last week, I have show you the derivative of the log. It's quite different here. For example, let's say if you refer to page page number 4 and 5, derivative of log function and derivative of log and exponential. For example, let's say we have in the line is slow here. Okay. For log function, let's say we have y equal to log 2x. The first derivative dy dx or y prime, this is equal to 1 over x log 2 logs 2e. There's the derivative of for log function. You can refer to page number 4. And for exponential function, let's say we have the exponential function. Let's say we have y equal to e to the power of x squared plus 3. The first derivative y prime, this is equal to as you can see on you can refer to page 6. Okay, this is equal to e to the power of x squared plus 3 ln e and we need to find the derivative of x squared plus 3. This is 2x. So the answer is we can arrange this. Okay, please remember ln e. This is ln e. This is equal 1. So the answer is the first derivative of this function is 2x e x squared plus x squared plus 3. Okay, that's a few example that related to the first derivative of related to the differentiation. Okay, for today I will continue to part B. That is related to the increasing function and decreasing function. The application of the application of differentiation. Okay, when we find the differentiation or dy dx, the value of the differentiation, the dy dx, the differentiation, the first difference, especially the first differentiation, dy dx or y prime or f prime x. Okay, this the value of the differentiation uh, is also equal to the slope of the function. If the value of the the in other words, the the value of the value of the differentiation is also equal to the slope of the tangent line. If the first differentiation is positive, if the value of the differentiation is positive, we can say that the tangent line has the positive slope, or in other words, the function is increasing, or the positive slope, the positive value of first derivative, the positive value of the first derivative is also related to the positive slope of the tangent line. In other words, when the slope is positive, that refer to the situation where the function is increasing. As you can see in this graph, graph A and graph B. For this situation, all the first derivative is positive. Okay, and then if the first derivative is negative, the negative value of this dy dx is also refer to the slope of the tangent line is negative. In other words, the function is decreasing. That's the positive what the use of the application of the derivative dy dx. Okay, for example, let's say you can refer to the page 1 part B. Let's say, okay, I would like to explain this function. Okay, let's say we have this quadratic function. Please refer to page 1. Let's say I will write again this function. Okay, let's say, for example, we have y of fx equal to x squared minus 5x plus 6. There is a quadratic function. The first derivative of this function y prime or dy dx, okay, this is equal to 2x minus 5. 2x minus 5. Okay, let's say this equation, the first derivative of this function, the first derivative of y, that is 2x minus 5, is also known as a slope equation. It's also known as a slope equation. But now we want to determine where the function is increasing or decreasing. We just want to identify where the function is increasing or decreasing. Okay, since there is a quadratic. If you refer to topic 1, there is a quadratic function. For this quadratic function, we know that for this quadratic function, the a is 1, b equal to -5, c equal to -6. Okay, the a is positive. The a is positive 1. A is a positive 1. In other words, the function is uh, uh, open upward, open upward, if because the a is positive. The graph is open upward. So if you refer to this graph, okay, there is a fx. The graph is open upward. Uh, this graph has two situation here. The first part of the graph is decreasing. This area decreasing. The second part of this graph is increasing. This one. Uh, uh, Now we would like to identify uh, where the function is decreasing. What is the value of x? There must be a borderline, the turning point here. We want to know the turning point here. What is the turning point, the critical point, where the graph change, the slope of the graph is changed from, for example, from negative to positive. Okay, in this area, from this area, we can see here the graph is increasing, so decreasing. The graph is decreasing after the let's say this x star. After the x star, the graph is increasing. In other words, for this part, the first derivative is positive. At this part, the first derivative is negative. So this graph has two area. The two area. The first area is decreasing, and then the second area is increasing. And then at before x star, we know before x star, the slope of the graph is negative. After x star, the slope of the graph is positive. Okay, x star is also known as a critical point. Critical point or turning point. Okay, at this critical point, at this turning point, is at x star, the slope of the function is equal 0. The slope of the function, the slope of the function, or the first derivative equal 0 at this point. Okay, at this critical point, we also known it as a critical at a critical point. Okay, now at this point, we first how to define this this area. Where what is the value of x? We want to identify the range, the zone area, the area where the graph is positive, has a positive slope, and the graph has a negative negative slope. So for example, for this example, we just take the first derivative again. What is y? Okay, y equal to this function is you can refer to page 1. It's x squared minus 5x minus 6. The first derivative, we need to find the slope equation. This equal to 2x minus 5. So in order to identify the positive, the negative area and positive area, the positive value of the positive value of dy dx and negative value, we need to find the slope equation, and the slope equation must equal 0. Just take the in other words, in this case, the slope of the tangent line, equal 0. The slope of the tangent line, equal 0. So what is the value? If 2x minus 5 equals 0, so 2x equal 5 and x equal to 5 over 2. Okay, in this case, the slope is equal, the first derivative uh, the first derivative uh, the first derivative is 0. when x equal to pi over 2. Okay. So at this point, the slope is the slope of the tangent line is equal 0. This point is also known as a critical point. Okay, this is a x star pi over 2 at this point. X star is 2 or 2.5. That's the critical point or the minimum point, the vertex point of the uh, uh, quadratic. So in other words, now we can identify for if we choose the value of x is less than 2. Let's say again f prime equal to 2x minus 5. Okay. Uh, at the critical point, 5/2. 2 times 5/2 times 5 equal 0. Okay, that is the critical point. The first derivative is 0. The slope of the tangent line is equal to equal to 0. Okay, let's say I choose any value of x, but the value of x is less than 5/2. Let's say I choose 5. Let's say I choose 0. If x equals 0, 2 times 0 times minus 5, the answer is negative 5, less than 0. The slope of the function is negative. In other words, the function is decreasing when x less than 5/2.5. But when I choose any number, if x equal 3, the value of x is greater than 2.5, what happened to this function? What happened to the slope of the function is 2 times 3 minus 5. Okay, this equal to 6 minus 5 equal 1. Okay, the slope of the function is greater than 0. It's positive. In other words, the function is increasing after uh, x equal to 2.5. So based on this finding, we can conclude here the function is increasing in interval. If you choose any value is less than 2.5, the function is increasing from the from range in interval 5 decreasing negative infinity until positive 5/2. The function is decreasing, but from 5/2 and until positive infinity, the function is increasing. Function is increasing. That's how to determine the positive area and negative area of the function. When the slope is positive, that shows that the function is increasing. But when the slope is negative, uh, that shows that the slope is the function is decreasing. That how to relate the differentiation with the slope of the function or the slope of the tangent line. Okay, that's about about the increasing and decreasing function. As you can see, you can refer to this page, part B. Okay, before I continue, okay, let's say for this for today okay, the next is uh, about the application of weight of chain, and also how to apply uh, this uh, this uh, this differentiation, how to apply differentiation in term of uh, weight of chain, marginal revenue, or in term of elasticity, and we have a demand elasticity here, and also okay, okay, before we continue to part C. Okay, before that, okay, I will explain about what is the weight, the weight, the weight of chain. Okay, here we have total cost. Okay, again we have total cost and total revenue. Yeah, okay. First derivative. Okay. Okay. Okay, please refer to page part B, part B, page 2. Let's say again, given the okay, let's say we have TR. What is TR? Revenue function. We have a revenue function here. What's the revenue function? It's a TR. Again, TR is equal to price times quantity for firm. Okay, let's say if TR is a revenue function, uh, the uh, the first derivative of the first differentiation of TR, or dTR dQ, or TR prime. Okay, the first derivative is also the first derivative equal to the marginal revenue. What is the marginal revenue? Marginal revenue is MR. Okay, marginal in based on the theory, marginal revenue equal to uh, uh, change in TR divided by change in Q. This will this marginal revenue will measure to the what happened to the total revenue when the number of when quantity change in 1 unit. If a firm increase the quantity by 1 unit, the total revenue will increase by MR unit. MR will measure the effect of the change, the effect of the quantity, the effect of the changes in quantity to the change in the total revenue. So in terms of dy dx, MR can be measured by take the first derivative of the first differentiation of total revenue. Okay, in other words, let's say I have this function. Assume that the total revenue equal to 30Q minus 0.3 Q squared. Let's say there's a total revenue. So MR, find the MR. What is MR? MR equal to the first derivative of total revenue, or TR prime, or equal to, or dTR dQ. Okay, we take the first derivative for 30Q. The first differentiation is 30 minus 0.3 Q squared. The first derivative is 0.3 times 2, 0.6. Q to the power of 2 minus 1 equal 1. Or it's not necessary to write this number, or 0.6 Q to the power of 1. Okay, this is the marginal revenue, or the slope. In this case, the marginal revenue is also known as a slope equation of slope equation of total revenue. That is the relationship between the MR and TR. So please remember, the first derivative of TR is MR, or marginal revenue. So since MR equal to 30, so MR equal to 30 minus 0.6 Q. That is the marginal revenue of TR. Marginal revenue in bahasa is hasil sud. So when Q equal, let's say when quantity equal 2, what is MR? Find MR. Let's say MR equal what? What is MR? So when Q equal to MR2 equal to 30 minus 0.6 Q 0.6 times 2. So the value of MR is 28.80. That the relationship between the MR and TR. So and the next one, let's say we have total cost. Okay, what is the total cost? Again, total cost equal to fixed cost plus variable cost. Let's say, for example, the total cost equal to 0.1 Q squared plus 3. 0.1 0.1 Q squared plus T. Okay, before that, since we have the TC, okay, this is a TC, total cost. Okay, the first derivative of TC prime, or dTC dQ equal to MC. What is MC? MC is a marginal cost. And marginal cost is based on the theory. Marginal cost, the formula for marginal cost is changes in TC, delta TC changes in TC divided by changes in quantity. In other words, the marginal cost will the marginal cost measure the effect of quantity on total cost. If the number of quantity if quantity increase by 1 unit, the cost will increase by MC unit. By MC. What is the value? The value of MC will measure the impact of quantity on the total cost. When firm increase the quantity by 1 unit, the cost will increase by MC, by marginal cost. The marginal cost will measure the effect of quantity 1 unit changes in quantity on the total cost. Okay, for example, let's say TC equal to 0.1 Q squared plus 3. So the MC, find the marginal cost. In order to find the marginal cost, we need to take the first derivative of TC, or dTC prime, or dTC dQ. Okay, find the first derivative of TC. TC equal to 0.1 Q squared plus 3. So the first derivative is equal to 0.2 Q. That is the marginal cost based on the first derivative of TC. So let's say, for example, if quantity equal 4, find MC. What is MC? MC when Q equal 4, this equal to 0.2 times 4. The answer is 0.8. That's the quantity of the value of MC when Q equals 4. In other words, when output or quantity increase by 1 unit, the cost will increase by 0.8, or RM 0.8, or 80 cent per 1 unit increase in quantity. Okay, that's the relationship between the TR and MR. TR and MR. TR, total revenue, and marginal revenue. The second one is about the total cost and marginal cost. Marginal cost, or cost suit for MC. Okay. The next one. Okay. The next is about the elasticity. Elasticity. Okay, what is elasticity? Please refer to page 3. Okay, elasticity measure the percentage change in quantity demanded to a given percentage change in price. In other words, the elasticity is E equal to the percentage change in quantity divided by percentage change in price of good. So in other words, if we want this elasticity will measure the what happened, what happened to the quantity. When the price of the good increased by 1 unit. If the price goes down, or if the price decreased by 1%, what happened to the quantity? We want to know how many percent changes in quantity for every 1% change in price of good. Okay, that is the basic formula of E, or elasticity. Elasticity. Percentage change in quantity divided by percentage change in price. Okay, in terms of derivative, in terms of dy dx, okay, these changes, this measurement can be calculated by using this formula. This also equal to the dq dp times p over q. That's the formula of elasticity in terms of differentiation. Formula kekeanjalan berdasarkan pembezaan. So in this class, you need to remember this formula. Okay, there's a formula that we are going to use in order to we are going to use when we want to measure the elasticity. You must apply the derivative in this case. Okay, this value, the value of E, can be positive and can be negative. But normally, in terms of interpretation, we take the absolute value of E. The absolute value of E. We just take the positive value of E in order to interpret what does it mean by how to explain the elasticity by using the E, the dq dp and p per q, by using the formula of elasticity. In general, when the value is less than 1, we say that the demand is inelastic. The demand is inelastic when the absolute value of E is less than 1. What does it mean by the demand is inelastic? Permintaan tidak anjal. That's refer to the percentage change in quantity less than the percentage change in price. That's when the price, in other words, the percentage change in price is greater than its percentage change in quantity. In other words, if let's say, for example, let's say the price of A is increased by 10%, but the quantity of demanded just decreased by, let's say, 5%. That's why in the case we can consider that the demand is inelastic. The percentage change of quantity less than the percentage change of price. Okay, the second condition is where the absolute value is positive. Is greater than 1. The demand is inelastic when the absolute value of the elasticity is less than 1. But when the value of the elasticity is, the absolute value of elasticity is greater than 1, okay, that refer to the situation where the demand is elastic. The demand is elastic. In bahasa Melayu, permintaan adalah anjal. Elastic or anjal. In this case, the percentage change in quantity is greater than percentage change in price. If the price is, For example, if price increase by let's say 10%, the price increase by 10%. In this case, the quantity increased, but let's say if price increased by 10%, the quantity decreased by 50%, for example. So the percentage change in quantity is greater than the percentage change in price. In this case, we can conclude that the demand is elastic. Permintaan adalah anjak. And then if the absolute value equal 1, so in this case, we can conclude that the demand is unit elastic. Unit elastic. The demand is unit elastic. When the value of the E, when E equal 1. In this case, percentage change in quantity, equal to percentage change in price. In other words, if price increase by 10%, the demand decrease by also 10%. So percentage change in quantity equal to the percentage change in demand. So in this case, we can say that the demand is unit elastic. The value of the elasticity equal to 1. Okay, that about the background of the elasticity. Let's take one example here. Please refer to page 5. Let's see, I have this P equal to, let's say, 20 minus 0.2 Q. Let's say we have this example. We have a demand function here. P equal to 20 minus 0.2 Q. Now we will have to determine, find, the question is, find the demand elasticity at Q equal 10. Find the demand elasticity at Q equal 10. So, given P equal to 20 minus 0.2 Q, to find the demand elasticity, okay, what is the formula for demand elasticity? E equal to dP dQ, dQ dP. The formula for elastic demand, dQ dP PQ. Okay, dQ dP P over Q. So the question is, we would like to find the demand elasticity at Q equal 10. When at Q equal 10. Okay, for this case, we need to find first the dQ dP and P over Q. Okay, what is Q? Okay, Q equal to 10. When Q equal to 10, P equal to 20 minus 0.2 times 10. This is equal to 18. When Q equal 10, P equal to 18. Now we know P equal 18. Okay, and P equal 18. Q equal 10. Then we need to find dQ dP. What is dQ dP? There is also dQ dP is also the first derivative, but for this case, from this equation, we can find dP dQ. Please remember, when we're talking about first derivative, dP dQ, P is a dependent variable, Q is a independent. Q is domain, P is range. We have domain and range, and also input and output. So from this equation P equal to 20 minus 0.2 Q, we can find dP dQ. dP dQ from this equation, we have a 20 minus 0.2 Q. So dP dQ equal to negative 0.2, because we have constant here. We have constant 20 equals 0. First derivative of constant is 0. And then the first derivative of negative 0.2 Q, the first derivative Q equal 1. And now we only have negative 0.2 only. So that is the first the first derivative of the demand equation. So we have dP dQ, but from this formula, for the elasticity formula, we need dQ dP. From equation, we have dP dQ, but to find the elasticity, we need dQ dP. So based on the rule of differentiation, we have inverse rule. In other words, dQ dP, this equal to 1 over dP dQ. 1 over dP dQ. Based on this example, dP dQ is negative 0.2. Okay, that's what. So therefore, dQ dP is 1 over 2 negative 0.2. Okay, so therefore, the elasticity is dQ dP 1 over negative 0.2 times P per Q. P is 18, Q is 10. So the answer is a 9. It's a negative 9, because we have a negative here. Negative 9. And in order to interpret what does it mean by negative 9? The interpretation, terjemahan. What does it mean by negative 9? Okay, so in order to interpret this value, negative 9, we need to find the absolute value. The absolute value of E equal to 9 and less than 1, greater than 1. Positive 9 is greater than 1. So we can conclude that the demand is elastic. Permintaan adalah anjal. Demand is elastic. What does it mean? What does it mean by 9? This number 9. Since the absolute value is greater than 1, we can conclude that the demand is elastic. And we can also interpret this value 9 as a 9%. This value 9 is also 9%. This 9%, what does it mean by this 9%? Okay, we can say that at quantity equal 10, at this point, if at Q equal 10, 1% increase. 1% increase in price in P will lead to 9% increase. 9% increase in quantity. Demanded. That's how to interpret the value of elasticity. The demand is elastic. At Q equal 10, 1% increase in price will lead to the 9% increase in demand. In this case, percentage change in quantity equal 9%, but percentage change in price is 1%. Percentage change in quantity is greater than percentage change in P. That's why the demand is elastic. The price of the good only increased by 1%. but the quantity demanded increase by change, maybe decrease in decrease in decrease in 9%. It's not increase, decrease. Decrease in 9%. Okay, I went again here. Will lead to the 9% decrease. Decrease in quantity demanded. Decrease in quantity demanded. That's why the value is, the real value is negative. We just take the positive value if you want to interpret the elasticity value, 9%, negative 9. Okay, that's about the elasticity, So that's how we can apply this concept of elasticity. We can apply differentiation in elasticity, marginal cost, and total cost. Okay, any questions so far? I hope everything is clear. Any question?
No, doctor.
Okay, the next part. Okay, that's all about the part B. That's all about the part B of this topic. Okay, the next one is a part C. Okay, the part C is very interesting. We can apply this concept. We can apply differentiation in terms of slope of the tangent line. In other words, we can find the optimization point of the function, or we can find where the relative maximum or relative minimum of the function. Okay, I will refer to the part C of this topic. Okay, again, as I said earlier, uh, the first derivative or the first differentiation is also equal to the slope of the tangent line. When the value of the value of first derivative is positive, we can conclude that the slope is increasing. The graph is increasing because the slope is positive. But when the value of the when the first derivative is negative, the graph is decreasing, atau semakin berkurangan sebab slope dia adalah negatif. That based on the first based on the first derivative, dy dx. The value of the first derivative can be positive and can be negative. The value of the first derivative is useful when we want to find the slope. If we want to determine whether the function is increasing or decreasing. Okay, that's the first part. The second derivative is also important because the second derivative can be used to measure the concavity or kecembungan or kecekungan. Concavity. We have two situation here. Concave up. Concave up is a cekung ke atas. Concave up and concave down. Concave up and concave down. Cekung ke atas or cekung ke bawah. Okay. Now there's a concave, in this case, there is a concave up, concave up. Okay, this is a concave up. The cone ke atas, when the second derivative, f double prime is positive. It's the graph is cekung ke atas. The graph is a concave up. The shape of the graph is like a U shape. When the second derivative is positive. But when the second derivative is negative, this one, the second derivative dy dx f double prime x negative, we can conclude that at that point the graph is concave down. So that the use of second derivative in order to determine whether the graph is concave up or concave down. In other words, in topic 1, based on the if you refer to the quadratic, there are two shapes of quadratic function, whether the function is downward sloping or upward sloping, based on the value of a. In general, we can apply the first derivative and second derivative to identify whether the graph is concave up or concave down, based on the value of based on the second derivative. Okay. I would like to let's say I would like to explain this general. Let's say I have one function here. Say for example, okay. Please refer to the additional file. Let's say I have the additional file here in UKM folio. You can refer this file. Different cubic graph. Okay, that's why the graph. Okay, I will show you how to apply the first derivative in terms of the how to use first derivative and second derivative in order to identify whether the graph is increasing, decreasing, whether the graph is concave up or concave down, or in other words, we want to know what is the maximum or minimum point of the graph in terms of relative maximum or relative minimum. You can also refer to part T of topic 6 from page 1, 2, 3, 4, 4, and also 5, 6, and 7. Okay, let's say I just apply this figure. Let's say, okay, I would like to screenshot this page. You can download this file from UKM folio. Okay, let's say I hope. Yeah, like to. Okay. Okay, this graph, we refer to this graph. Okay, for this graph, let's say we assume that there is a one graph here. We can see here the when we move from x, let's say from left to right. Let's say we assume that we move from left to right when the value of x increase. The value of x increase from left to right. What happened to the function? When the value of x increase, let's say from negative to positive, we can see here, we can clearly see here the graph is increasing. Sorry, the graph is decreasing. For this area, the graph is decreasing, and then after the let's say after the certain value of x, maybe x equal to -3, the graph is increasing until the 1 point, and then the graph decreasing again. Okay, that is the movement of the graph. There is show the movement of the value of y when x increasing from the left to the right. Okay, now I would like to explain this graph in terms of dy dx. Okay, in terms of slope. Okay, let's say I just divide this graph for let's say I just divide the graph into let's say this area, first, second, this. Okay, let's see. We have area let's say A, B, and C. Let's say C. A, B, and C. Okay, when we move from area A, B, and C. In area A, we can see here the slope is the function is decreasing. The function is decreasing. In terms of slope, the slope of this function is negative. The slope of the function is negative at this area. And then the first derivative, in terms of the first derivative of the slope is also negative for area A. And then for area B, we can see here the value as the value of y as the value of x increase, the value of y also increase. There is a positive relationship between y and x. X increase, y also increase. But and then that's mean the slope of the function in this area is positive. The slope is positive. So since the slope is positive, the slope is also we can also assume that slope the value of the slope, if the value of the slope is positive, the value of the first derivative also positive. So for the in this area in area B, the first derivative of x is positive. The area of the first derivative of x is positive. Same goes to the C. As the value of x increase, the value of y decrease. There is the negative relationship between x and y. In other words, in area C, the slope of the function is negative. So if the slope of the function is negative, we can also conclude that the first derivative of the slope in this area is also negative. Okay, that's how to apply the first derivative in terms of slope, because the first derivative is also show the slope of the tangent line. In other words, when we find slope, we can also find the first derivative. The first derivative of the function is also show the slope of the function. If the slope is negative, the first derivative is negative. When the slope is positive, the first derivative is also positive. Okay, so for this graph, we have when we move from A, B to C, the sign of the slope is changed from negative, positive, and negative again. That's the situation of the graph based on this based on dy dx or first derivative. Okay, now, okay, I would like to refer to the there are 2 points here. When we move from negative to positive slope, from area A to area B, the slope of the function change from negative to positive. So basically there is 1 point here. You can see 1 point here. When we move from left to right in area A, the slope is negative. At this after this point, let's say I choose it. Let's say x1. At this point, before x1, the slope is negative. After x1, the slope is positive. This x1 is also known as a critical point. Critical point. Also known as a critical point. Okay. At this critical point, the first derivative equal 0. The slope of the tangent line is equal 0 at this critical point. Okay, that's one critical point here. Okay, we have another critical point when we move from B to C. When we move from B to C, the slope change from positive to negative. So we have a second point here, x2. This is also the critical point or the turning point. The turning point is what? The turning point, in other words, the critical point is a 1 point here, where this point is a borderline. It's a separate the positive and negative area. The separate the it's a borderline. It's a border between the positive slope and negative slope. Again, at this critical point, you must remember this. At this critical point, the slope of the function, keturunan fungsi, the slope equals 0. In other words, the first derivative equals 0. The first derivative equals 0. That is the first derivative of the function equal 0. Okay. So that is the critical point. Okay. Now I will apply the second derivative. The second derivative. Okay. X2 is critical point. X1 is also critical point. Both has the positive as a 0 slope. The slope at critical point always equals 0. The slope at x1 equals 0. The slope at x2 also equals 0 because x1 and x2 is a critical point. But we can clearly see that the difference between x1 and x1 and x2 are critical point. What is the difference between x1 and x2? As you can see here, x1 is a minimum point. It's a minimum point, minimum relative point, but the x2 is a maximum point. That the difference between the x1 and x2. Both are critical point, but when we see in the graph, x1 is a minimum point, x2 is a maximum point. So in terms of dy dx, the second derivative of fx must be in other words must be if you refer to this concave down, is negative. The graph is concave down. So that's show that if the first derivative is 0, the second derivative is negative. Okay, at that point is also known as the maximum point, or the graph. We can conclude the graph is concave down. You can refer to page 7, how to identify how to identify the maximum or minimum point. Whereas on the other hand, at point x1, x1 is also the critical point, but x1 is also is as you can see in the graph, the x1 is a minimum point. The first derivative for x1 is 0, but the second derivative of x at this point, let's say x1, is positive. So we can conclude here, the graph is concave up. So that point x1 is a minimum point. Okay, that's the rule. You need to remember this rule. The relationship between the maximum point and minimum point. What is the difference? How to identify that critical point is a maximum or minimum? We need to find the second derivative. We need to find the second derivative of at that point, whether the second derivative is positive or negative. Okay, so this point is also can be identified uh, by analyze the change in slope, the change in slope. So let's say if before x1 the slope is negative, after x1 the slope is positive. So the movement is from negative to positive. The slope is changed from negative to positive. So this change indicate that that x1 is also minimum when the slope change from negative to positive. But when the slope is the sign of slope change from positive to negative, we can conclude that critical point. We can conclude that the critical point is the maximum point. That is the second way, the second method, how to identify the maximum and the minimum point. First, you need to determine the critical point first by using the second derivative, where the value of the value of slope equals 0. And then the second one, you need to find the second derivative. If the second derivative at that point is negative, the critical point is maximum. But if the second derivative at that point is positive, we can conclude that the slope the point is a negative, is a minimum point. Or we just find the slope before and after critical point. If the slope is before the x1, if the sign of slope change from negative to positive, before critical point is negative, after critical point is positive, so we can conclude that the critical point is minimum point. But if the sign of slope change from positive to negative, before critical point the slope is positive, after critical point the slope is negative, so the critical point is the maximum point. That's how to apply this first derivative and second derivative in terms of maximum and minimum, relative maximum or relative minimum. Okay. For detail, you can refer to page 7. Page 7, step in determining the relative extrema, the relative point, by using the first derivative and the second derivative. Basically, there are first method and second method here. There are two methods here. I explained this method before this. The first derivative, we just check the sign. If the sign change from the sign of the slope change from positive to negative, the critical point is the maximum point. But if the slope change from negative to positive, the critical point is minimum point. Or based on the second method, we can use the second derivative. We just take the value of the second derivative. If the second derivative is positive, it's negative, the critical point is a maximum point because the graph is concave down. But when the second derivative is positive, you need to remember this. The graph is concave down, so the critical point is the minimum point. If that's the first method and the second method. You can use both, but if you fail to test by second method, if the second method is unable to identify the minimum or maximum point, we can apply the first method number one. We just find the second derivative, and we can just change. We just identify. We just check the change in slope from negative to positive or positive to negative. That's how to find, how to determine whether the graph has a minimum point or maximum point, or in other words, we want to identify the positive and negative area of the slope. Okay, then how to apply the concept. I will choose a few examples to explain this concept after break. Okay, since there is almost 9:30, I think we take a break for 20 minutes. Before we take a break, do you have any question before we take a break? After break, I will explain this example. Any question before we take a break?
No, doctor.
Okay, if you have no question, we take a break for 20 minutes. We will continue. We take a break for 20 minutes. We will continue our lecture at 9:50. Okay, we take a break for 20 minutes.